this is going to be a bit of a jump from what we just heard about solar systems and exoplanets to a totally different, yet also very exciting issue astronomy and physics are trying to come to grips with, and that's gravity. We know that Einstein's theory 100 years ago reformulated how objects with a mass interact with each other by stating that if you have a mass, in this case, one of these balls there, then if another mass comes by, then the space-time is changed, is perturbed by the masses, and as a result, the motion of another body here in this turquoise color is basically altered and reflects the interaction between the masses. Now that theory 100 years ago was a purely mathematical construct, and it took another 50 years by other theorists like Carl Schwarzschild, Roger Penrose, who also got the Nobel Prize last year, and Roy Kerr, and many others, to understand better what might, come out of this theory. Now, strangely enough, one of the things which emerges out of this is the concept of a black hole. Think of our sun. Our sun is obviously an object we know very well, about 600,000 kilometers in size. If you had a rocket on the surface of the sun, then we know that rocket has to have a speed of about 600 kilometers per second to escape the gravity of the sun. Now, in your mind, you can make a smaller sun with the same mass. Suppose you make it, only a few kilometers in size. Well, then gravity at the surface of that sun is much greater, and the escape speed now for the rocket is 300,000 kilometers per second. 300,000 kilometers per second is the speed of light. And we know from experiments, many experiments, that there is nothing which can travel faster than the speed of light. So an object which would have a mass of the sun and a size less than this 3 kilometers would actually not be visible. It would be a black hole. Now there's another prediction of the theory of Einstein, which says that in that case, all of the mass of the sun would be collected in the very center, in the density, infinity singularity. These are, of course, spectacular predictions, and it took a long time before these mathematical predictions became testable by measurements. Do these black holes exist? Now, how would you find something which you can't see? So suppose you had a sun, which is a black hole, as I just explained, orbited by planets. Well, the planets would move according to Newton's or Einstein's theory, whether or not the sun shines. So by observing objects in the vicinity of a big mass, including a black hole, can be used to infer the mass. And if you can come very close to the object, you can even infer whether it might be a black hole. So that's what astronomers have been trying to do since the 1960s, when at that time, the quasars were discovered. These are very bright radio-emitting objects which turn out to be the cores of very distant galaxies, very brightly shining. In this particular case, which was the first one which was discovered at a distance of 2.5 billion light years, so, a long distance away, the luminosity of that object is actually 1,000 times the entire Milky Way. And the proposal, theoretically, what that might be, are actually, paradoxically, black holes which are accreting. So before the material disappears in the event horizon, which I described before, the gravitational energy can be converted into heat and radiation, and that radiation can be detected. But that's a theory. How do we possibly prove it? So much effort has been spent in the last 60 years to go at the bottom of this. And it's only been the last few years, in fact, that we've had several experiments coming to much progress to, in fact, show that these massive black holes do exist. And I'll describe the experiment which I've been involved in over the last 40 years. Now, quasars are very distant objects, as I said, and it's hopeless to try to see motions around them. So it is necessary to come to much closer objects. And the closest galaxy we have is our own, the Milky Way. Now, in the Milky Way, we cannot look at this directly with visible telescopes because of dust extinction, but we can look at it in the infrared or in radio waves. And when we look there, we find a very dense star cluster here in blue, about 1 million times more denser than the solar neighborhood. And surrounding that star cluster, there is a whole collection of various gas clouds, which you see in green and pink. And it is these gas clouds which, in the first set of experiments in the 1970s and 80s, were the test particles to measure the mass of the center. Now, this was done in Berkeley by Charles Townes, a Nobel laureate, who won the prize for the invention of the maser and the laser, and in his later years got interested in astronomy. I joined that group then as a postdoctoral fellow and then faculty member, and we carried out experiments in the infrared to measure the motions of these gas clouds. And what we found was that at large distances from the central position, which you see demarked here as Sag-A star, where there is a very compact radio source, the mass increases as you go out. That's basically the extended star cluster. But then inside of about 3 light years, 1 parsec, the mass does not change and appears to be several million solar masses. So in the 1980s, we had the first evidence that perhaps there could be a compact object of a few million solar masses, plausibly associated with a radio source and perhaps a black hole. But in order to actually, prove that, you have to make much more precise measurements. Gas clouds are not necessarily the best ways of tracing gravity. So it took, in fact, 40 years to get from that first indication to where we are now. Lots of technology had to be developed. New detectors had to be built. Adaptive optics had to be invented in order to correct for the distortions of the waves, which as they penetrate through the atmosphere, make images unsharp. And so with adaptive optics, you basically measure the fluctuations and then correct them with deformable mirrors so that you get sharp images as if you have telescopes in space. Also, another important part are big telescopes, because you want to have high angular resolution to see very fine and sharp imagery. So the field I'm talking about very much depends on the development of ever more complex technology and sensors, adaptive optics, and big telescopes. Now, 2 groups, one in Europe, using the telescopes in Chile of the European Southern Observatory, and one on Mauna Kea using the Keck Observatory, in the 1990s began looking at stars as tracers. And after a few years, we saw the first motions, which confirmed indeed the evidence I described earlier, that on the scale of a few light years, there is this 4 million solar mass concentration. But, and that was the surprising thing, the motions of those stars, some of the stars, were so close to the central radio source that they might, in fact, give us more precise information through orbital motion. And indeed now, 20 years later, we have several stars, in particular one, which orbit this central radio source Sagittarius star on a highly elliptical orbit and come close to it, as close as the solar system scale, about 3 times the Neptune orbital radius, and move there with about 8,000 kilometers per second. So within 17 light hours, we now know the 4 million solar mass object which we had seen before must be included. So clearly, this is a very strong, plausible explanation if this object is a black hole. But must it be a black hole? One of the assumptions we are making is that in order to make these conclusions, that general relativity holds on these scales in these very extreme environments. So we need to actually ask, can we test general relativity 26,000 light years away from us in the galactic center? And yes, we can, by using ever more precise methods. And one of the methods which we've been developing in the European Southern Observatory is interferometry. So instead of one of these 8-meter giant telescopes, we combine the light, like in radio interferometry, to basically create what is a super telescope, a virtual telescope of 100 and more meter diameter, and therefore 20 times higher angular resolution. So with that, we can see the motions of the stars with exquisite precision. And in fact, the star which I showed you has a period of 16 years. So when we saw it first come close to the galactic center in 2002, we then knew it would be coming back in 2018. So both the Keck group and our group were ready then in 2018 to look at the motions of the star very close to the black hole. And with interferometry, we can now see this motion, not from year to year as before, or from month to month, but from day to day. And this is indeed what happened right around May 9th, which was when the star came closest, 17 light hours, as I told you. And the precision of the measurements which both our group and that of the Keck group obtained were now good enough to make several tests of general relativity. One of the tests is that clocks near a heavy mass go slower. That's called the gravitational redshift. Another test which we were able to do is to show that the orbit on which the star S2 is orbiting is not closed, it's precessing. That's called the Schwarzschild precession, and is an effect which only occurs in general relativity. And finally, we've been seeing gas clouds very close to the event horizon with speeds of about a third the velocity of light. So all of this is qualitative and quantitative evidence, number one, that general relativity holds in these extreme environments, and that indeed Sagittarius star is likely a black hole. We now know the mass of that black hole to a small fraction of a percent, and we know that it must be enclosed within, about a few times the event horizon size. So as I said, this is a very good, quantitative proof that these black holes indeed exist. Now, are we done? No, because the theory of Einstein is incomplete. The proposed singularity of the mass at the very center is likely wrong. There must be quantum effects. And it is very interesting to look into the future and use still better method, including gravitational waves in space, for instance, to try to test the theory ever more precisely, and perhaps seeing deviations. But we can be happy at this stage. Much has been achieved with the ingenuity of many people. Several groups in the world have repeated the experiments. 2 groups have been repeated the experiments. And the future in this field, very much like what we heard about the exoplanets, is very bright. Thank you very much.